Hi there. Welcome to Climate Chat. My name is Leon Simons. I'm here with Peter Cox. It's great to see you, Peter.
It's a
Thank
pleasure.
you for coming on Climate Chat. And I just want to start this conversation by talking about the first time I learned about Peter's work. And that was when I read this book. This is the Dutch version. It's called De Laatste Generatie, which is a translation of this book by Fred Pearce, The Last Generation. And that it was published in 2007, and that really got me interested in climate change. And that's when I did. This Dutch book was only €5, and I think I gave 20 people a copy of the book. And I just want to read, and Peter is covered quite a bit in the book, and I just want to read what Fred Pearce wrote about Peter at the time, and then maybe Peter can talk a bit about what he's doing now after since 2007. So it says Peter Cox, UK Centre of Hydrology and Ecology in Windfrith, innovative young climate modeler of the likely impacts of aerosols in keeping the planet cool and the risks of land plants turning from sinks to a source for carbon dioxide later this century. I think that's also quite a bit of what we'll be discussing today. And yeah, hi Peter, can you talk a bit about what happened since then?
Well, as you can see, I'm no longer a young climate scientist, Leon. I'm quite an old climate scientist. But yeah, I'm interested in similar things. I suppose more and more I've got interested in how we might reduce the uncertainty in some of these things by looking at observations and models together. But I'm still very interested in the whole issue of whether the land carbon sink that's been absorbing about a quarter of our emissions could turn into a source in the future. And things like how resilient the Amazon rainforest might be, or actually how vulnerable it might be to climate change. And also the impacts of aerosols, and more interested in the impacts of aerosols, because I think we're in an interesting time in the climate, and that some of the things we're seeing are actually a combination of increasing greenhouse gases, especially carbon dioxide, also reducing aerosol concentrations, especially sulfur dioxide that leads to sulfur aerosols. So yeah, as your career goes on, you kind of leave things and come back to them. So it might be a sign that I'm getting towards the end of my career. I'm coming back to these things that Fred was talking about then, but in a slightly different perspective. When Fred was talking about that, when we were talking to Fred about it in this meeting, we were thinking about the situation where sulfur aerosol concentrations were going up and suppressing global warming and hiding global warming. And now we're in a situation where sulfur aerosols are thankfully coming down, CO2 emissions, and we're in the other situation where it's possible that some of the warming is not due to greenhouse gases, but due to this hopefully temporary effect of aerosols. But the jury's out still on that.
Yeah, I think there was what I read in the book was quite shocking. I think it was, and now I just went back and looked at the paper he referenced there, and there was. Let me share the paper here. There it is. I think this is the paper you wrote after a meeting you had where Fred Pearce was also attending, where you learned about the. I think who was there? There was a Dutch scientist was there. The Nobel Peace Prize winner Paul Crutzen.
He was there. Paul Crutzen was there indeed. It was a Dahlem conference on the outskirts of Berlin, and they used to run them where they basically lock you away for a couple of weeks, and you'd write a book, or you'd write chapters of a book. And Paul was there, and Andy Andre did this work with us. Andy's in one of the Max Planck Institutes in Germany, and Chris Jones is still at the Met Office. Did a lot of the modelling work. It's very simple modelling, so it was a proof of principle really. But the idea that if you had strong aerosol cooling, then when it came off, when we started to reduce sulfur dioxide, then we would get an enhanced warming, and that was what that was about really. But also it was about this idea that if you wanted to work out how sensitive the climate was to CO2, you have to account for the fact that there's also this counteracting cooling effect from aerosols. And it was quite strong at that point. Up to the 80s, sulfur dioxide emissions have been going up globally, and now they've peaked and come down, and then had a second peak, I think, with China, and they're coming down again. So there's a very big impact of aerosol changes on the climate that I think we sometimes forget.
Yeah, and I think so. So maybe you can explain a bit about aerosols. We've talked about that a lot here, but just give a short summary about what are aerosols and how do they impact the climate.
So aerosols are particulates. In the case of sulfur dioxide, it produces sulfur aerosol, and that is reflective, so it reflects sunlight. But also, what it does, and most importantly of all, what aerosols do is to act as cloud condensation nuclei. That means droplets can form more easily in clouds. It means clouds have more drops, and therefore they're brighter. So when sulfur dioxide was going up, clouds were getting brighter, possibly living longer, mainly getting brighter, and that was acting to cool the climate a little bit and counteract some of the CO2-induced warming and the greenhouse gas-induced warming. And as we've started to deal with sulfur aerosol, because we don't want sulfuric acid in our atmosphere, even at low concentrations, and we don't want the air quality problems, then we have revealed additional warming had been hidden to us from us by the fact that we were burning sulfurous coal, for example, that was both carbon dioxide that was warming up and SO2 was cooling it down. And we're now in a situation where we've actually not dealt with the climate problem, but we have dealt with the air quality problem to a large extent in most locations, and sulfur dioxide is going down. And that means that we're getting a unfortunate impact of that on additional warming.
Yeah, so these sulfur emissions are a byproduct of the burning of fossil fuels.
Yeah.
And now we can easily reduce those sulfur emissions, but reducing the greenhouse gas emissions is much harder.
Yeah, well, it has been, and they're longer lived, of course. So if you were to completely cut CO2 and SO2 at the same time, the SO2 effect would be quicker, because it's, especially in the lower atmosphere, very short lived, whereas CO2 has decades to century timescales to come out. So we're in this situation where the warming pollutant lasts a long time and the cooling pollutant doesn't last long. So when you act on it, you get an immediate impact of that. And there's reasons why we do that. And it would be crazy. Some people have argued it'd be crazy to put sulfur dioxide back into our emissions, but there is a consequence of it that we have to sort of understand and be ready for.
Yes, thanks. Yeah, and I think what I found really interesting from this from your research 20 years ago was that it showed this graph, and that's also what Fred Pierce wrote about, is that you could see almost if you have these high emission scenarios and high climate sensitivity, we could have almost 10 degrees Celsius of warming in the year 2100 already, right? And almost all these scenarios, if the climate sensitivity it turns out to be very high, in almost all scenarios we'd see over 6 degrees Celsius of global warming, which is more than what the world cooled during the last glacial period, when sea levels were 130 meters lower than today. So
for sure, there's a very simple modeling there, Leon, and I think if we did it again, we probably wouldn't get such large values. But it does basically say that if you imagine that the total energy you're putting in the form of what we call radiative forcing is low, and you have a certain amount of warming, it implies the system's very sensitive to that input radiative forcing. And that was basically what we were doing. We're saying that the aerosol forcing could be so large, it almost counteracting completely the greenhouse effect. And that means in order to get the warming we'd seen even up to then, the climate sensitivity would have to be really high. But at that stage, we were thinking aerosols were going up and they would come down later, but they actually already started to come down at that point, quite strongly from the 1980s onwards with air quality controls. So we've already been in a situation where we've got additional warming associated with cleaning up the SO2 from our air. And you can see it in the Ceres satellite record very clearly, actually, even from 2001 onwards.
Yeah, I think that's... Yeah, one more question before we get to that on this graph. So how likely, with the knowledge you have now, or how unlikely do you think it is that we will reach 6 degrees Celsius of higher by the end of this century?
I think it's unlikely, basically because we're over the hump with regard to SO2 and we're coming down the other side. So the warming we're getting is an amplified version of greenhouse warming, but I think it's still open. So as you've discussed yourself, Leon, the Ceres satellite record that tells us how much energy is going in and out of the climate system is quite alarming in that a lot of energy is going in, but also the planet's getting darker, which means it's absorbing more of the primary energy, which is the solar radiation. And whether that's feedback or forcing really determines what the future of the planet looks like. And I think we're still grappling with that. But what it seems to me at the moment is that the aerosol forcing is probably more important than we generally give it credit for, because the long-term warming is almost entirely correlated with greenhouse gases, especially CO2. But the short term seems to be very strongly influenced by these aerosol effects, especially when, for a while, sulfur dioxide and CO2 were going up together, as we actually showed in that paper, and then they decoupled, and now they're decoupled very strongly, and that means you're getting both. You're both getting an increase in the warming agent, but especially a decrease in the cooling agent. And because SO2 is short-lived, the second one is actually quite a large effect and fast change, I think.
Yeah, and I think was that in the New Scientist recent article where they quoted you saying that more of the warming in the past 20 years is due to, or I think up to 2019 is due to sulfur reductions than increasing in CO2.
I think so. So that, and normally the way that's done is that you make a sort of bottom-up calculation of how much impact sulfur dioxide could have had. But I think if you look at the satellite record, you can show, and I can show you a picture of this if you like, that most of the warming, well, the largest part of the warming is due to the planet getting darker rather than it getting less effective at emitting long-wave radiation, which is what you would expect if it was a greenhouse effect. So the greenhouse effect is kind of building up the blanket, and the sulfate reduction is a bit like making the blanket darker, so it's absorbing more sunlight. And what we see is the darkening is the key driver of climate change over the CIRAS record. So I think it's larger than the greenhouse gas change over that period, even though the greenhouse gas change is responsible largely for the whole changes, because the SO2 is going to go up, has gone up to the 80s, hiding some greenhouse effect, and then it'll go down again.
So I think that's an important point, where it's in the absence of greenhouse gas reductions that this sulfur is causing warming, right?
So it's indeed. And that's generally an issue because we find it easier to act on things like SO2 than CO2, and because of this nature of the CO2 being so long-lived.
Exactly. I think if you have a nice graph for that, I have many graphs covering this, but if you have one.
Yeah, sure. I'll try and load something up. Just let me get this started. If I just share my screen here. Can you see that okay? It's probably in
almost there. Yeah, you can you make it full screen? Yeah, there it is.
Yeah. So can you see the whole screen now?
Yeah.
Okay. So just stuff you know about this one's interesting, of course, and be familiar to you. The planet is, the evidence of climate change has never been clearer. I think that's really true to say. Last 10 warmest years, the hottest on record globally. 2024, the first one that definitely burst through the 1.5 target. It's a sort of aspirational target of Paris Climate Agreement. And as we might come to later, the really weird thing about those years, especially 2024, is how warm the ocean is. So generally, when there's variation in the system, it tends to be dominated by the land and the atmosphere, which are fast to respond. They've got a lower memory, but the ocean is really one that's been warm. And I'm going to just show you this picture and get to the crux of the matter. So this is just to show the aerosol effects we spoke about.
Yeah.
The main thing is that you create additional cloud condensation nucleus, so more droplets, and you get brighter clouds. This is called the first indirect effect. And also because the droplets are smaller, the clouds take longer to form precipitation. The drops have to coalesce to form droplets that fall under gravity and make rain. So you get a second indirect effect, but it's the first indirect effect that seems to be most important. So weirdly, we put out this polluting substance, SO2, pretty nasty stuff, and it makes clouds brighter. I think it's a certain irony to that. But you can see this is ship tracks before the shipping fuels were removed, SO2 was removed from them. But this is actually evidence of shipping tracks just off the coast of the UK where I'm living now, from a picture by that was provided, a satellite picture was provided by Jim Hayward at the university.
Very clear.
So what I was saying is that this is a best estimate of SO2 emissions, which lead to these sulfur aerosols that make clouds brighter. And essentially, globally, they peaked in around about 1980, and then they've been coming down. There was a secondary peak here, probably in about 2006, which I think was China, burning more sulfurous coal and then removing the sulfur. And this last bit is something you've spoken about, Leon, which is the possibility that the removal of SO2 from shipping fuel has had a bigger impact than we might have expected, because it was in a part of the world where there wasn't so much natural background SO2. But I think the jury's out on that.
Can you speak a bit about this non-linearity? Because I think it's I always find it a bit difficult to explain that to a broader audience, that this effect is not linear.
Yeah. So the impact of aerosols in general, these particulates in general, depends on how many particulates there are available already. So if you've got lots, the cloud will not be limited by these cloud condensation nuclei and therefore by aerosols. If you haven't got many, they will be. So there's a saturating effect of that. And over the ocean, there are some natural sources of sulfur, like DMS. It's produced by some phytoplankton, but they're pretty small compared to the polluted atmospheres that we have over the land, especially over industrial areas. So there's this tendency for relatively small changes to be more important in places that would otherwise be fairly pristine with regard to SO2. And I just was going to get to the crux. Oh, this is the figure that I was going to, on planetary darkening. So this is the amount of shortwave radiation, basically sunlight, that's reflected back to space by the planet as a whole. Started at about 100 watts a meter squared, is now down to about 97.5 in 21 years. And that doesn't sound like much, but this is 2.5 watts a meter squared, which is more than the CO2 forcing that's happened since 1750. This is not all forcing. Some of it's to do with the fact that the climate's changing and that's affecting clouds, but most of it looks to be. So that's a big change. And what this means for the climate depends on whether that's due to aerosols declining, for example, or whether it's due to a response to climate change itself, because we've had significant warming in this period. If it's due to climate change itself, it implies a really large feedback, and it would be worrying. It was a worrying situation for the Earth system. We'd be in a situation where we could be borderline unstable, which I think is unlikely, given we've had a stable climate prior to the pre-industrial. But what we can do from the satellite record, Leon, is to break down what's caused the global warming that I spoke about to start with. So that's the black line, the total global warming. And we can work out how much of this is due to for example, the sun's power changing. That's the dark blue line. That's pretty tiny. How much is due to what you might think of as the greenhouse effect, how effectively or how large the blanket is that's storing energy due to greenhouse gases. How much is due to the imbalance, which is the net top of the atmosphere imbalance, and this is sort of stored warming that we'll get later, if you like. You can think of it that. And then how much is due in the blue dot dash line to the reflected shortwave, this darkening of the planet. If you look at that, to a large extent, most of the warming is due to this darkening. So the greenhouse effect is always warming, and in the long term it dominates. But over this period here, according to the CERA's record, the key warming component is actually this fact that less light's being reflected from the planet as a whole.
And thus more absorbed.
And more absorbed, and that of course warms up the planet. You know, if you make the planet darker and it absorbs more sunlight, that's a primary driver of warming. So and this is just based on simple energy balance arguments and the top of the atmosphere fluxes. So it does depend on the CERA's record being reliable in this sense. But it does seem to me that it's fairly clear that if you look at the fluxes from CERA's at least, it's the darkening that's really driving the recent warming, and most of it anyway. And the only other thing I would say about that, and this is, we can come back to this if you like. So there's two reasons why the planet could be darkening. One is that there is a forcing agent like sulfur dioxide that's dropping off. And the other is that the planet is responding to global warming by changing its darkness. For example, clouds could be declining under global warming, and that's what happens in some models. So if more and more of this darkening is feedback shown in the right-hand side here, actually the estimate of climate sensitivity blows up. And this looks a bit like that paper you discussed that we published in 2005, but it's now SO2 going down rather than SO2 going up.
Mm-hmm.
The only way I can really square this with estimates of climate sensitivity based on many different bits of information, which is shown in the grey, is if most of this darkening is actually not feedback but forcing, which means that the SO2 decline has to be very significant, I think, in order for this to make any sort of sense. If it's all dark, if it's all feedback, the planet's in an unstable regime. So I don't think it could be that. But it does mean that knowing how much of this is feedback is absolutely critical for knowing the number one unknown really in climate change, which is how sensitive is the climate to relative forcing and therefore to things like CO2.
So in a way, you are also saying that if it's due to sulfur dioxide, reducing sulfur emissions from industry and from shipping, that would be in a way good news, because that would mean that we still somewhat understand what's happening.
Yeah, and it means that the long term, indeed, and it means the long term. So we'd be down in the grey zone, or possibly down to the left of it, and the long term warming would be as we expected. Sort of what's called an equilibrium climate sensitivity. Global warming due to doubling carbon dioxide of about 3 degrees. That's what we might expect given all the evidence we can see. And then we'd be in a place that at least we understand, although we get in this short term acceleration of warming because of aerosols dropping off. If we're, on the other hand, in the case where this is all feedback, we're in a place where some models there are some climate models are now saying climate sensitivity could be 6, but they don't look consistent with the observational record. They warm too much during the historical period. So I think you're right that if it's forcing, it's good news in the sense that this is a temporary thing as SO2 is removed from the air. If it's feedback, it's really bad news. So one of the things we're trying to do now is to work out whether we can work out where we are on this x-axis here on the right-hand plot to work out what the satellite record means for the climate sensitivity. I think that's the key thing there.
Okay, so you're still writing this paper, you're still doing this research.
Yeah, we are. It's very active research. I've got a PhD student trying to look at the patterns of SO2 reductions and albedo changes to see if we can work out how much of it is due to SO2 and how much of it isn't, and then we'll be able to at least have an idea on that. But it is a kind of paradox, this, because if you look at models, climate models and Earth system models have a range of climate sensitivity, going from somewhere like 2 to 6. The models that look more like the global warming record, they can reproduce the global warming record best, tend to be in this grey zone here, so sort of somewhere around 3 degrees for a climate sensitivity. But the models that darken, like the observational record, tend to be around 5 or 6. So this is where the paradox comes in. If you look at the satellite record without thinking about how the darkening could occur without high climate sensitivity, you might conclude sensitivity is high. If you've got the global warming record, you might conclude it's low. And that's what got me interested in this, really. I probably should come back now. So that's the nature of the paradox, really, that the observed record of global warming suggests that the Earth's climate sensitivity is at the lower end of the range produced by Earth system model sort of 3.
And that's over the period until about 2014, I suppose, right?
Yeah, the climate sensitivities are, of course, measured as if they are properties of the models. So each model, we can calculate the climate sensitivity by doing these idealized experiments where we double carbon dioxide and let it come to equilibrium. And then you have this large range. And when you look at those models, the ones that have got high sensitivity they overwarm during the historical period. And so you can reasonably, you might assume, if we have done, that climate sensitivity can't be as high as 6 because it isn't consistent with the observed global warming. But when you look at the albedo measurements, the ones that are in the reasonable range tend to be not darkening fast enough, and the ones that seem to be very high ECS are darkening quickly. So my and that's the nature of the paradox, is that observed global warming suggests low ECS, but observed planetary darkening suggests high ECS, unless the observed planetary darkening is not a feedback, that it's actually a forcing and it's due to sulfur dioxide reductions.
Yeah.
Stop sharing now so that we can talk.
Yeah, then we can.
Yeah. So yeah, as you sort of worked out, stop sharing here.
I'll move it. Yeah.
I've kind of come back to this story that Fred Pearce mentioned in that book from a slightly different perspective now, because at that time we thought high sulfur SO2 forcing must imply that climate sensitivity is high. Now, if SO2 forcing was high, the darkening since over the series record implies that climate sensitivity can be lower, because we've basically got a reduction in that very large cooling effect, and that's leading to some of the warming. But
But doesn't it also mean that the warming that wasn't the climate model that showed more warming than what was observed, were underestimating or the aerosol forcing?
It could be.
As you wrote in 2005, in a way, right?
Yeah, it could be. I think what happens in those models is they get darkening for the wrong reasons. I think they're getting darkening as the cloud feedback. There are cloud feedbacks operating, but in these high sensitivity models, which on the face of it have more realistic cloud models in them, there is a tendency for cloud cover to burn off, I think, especially low clouds in certain parts of the globe. And so what you're seeing in those models is that the planet darkens, but not because the clouds are getting darker, but because the clouds are disappearing. And that's not what the Cirrus record at least suggests. It pretty much says the cloud fraction globally is pretty much constant, but the clouds are reflecting less, like it's an SO2 effect. And so it does feel to me like working out why the planet's darkening is the key to the whole problem now.
Yeah, for sure. I fully agree with that. I think it's and I let me share one graph, because I think this is also really relating to, in a way, the acceleration question, right? And so I think what the way you're also looking at this acceleration is also more of in the fingerprints. So what is this acceleration? It's also an acceleration or an increase in how much sunlight is absorbed, while still there's an increase in outgoing long wave radiation. Let me share.
Yeah.
Graph. And I think what's really interesting, I have to update this, but can you see it? Yeah. What I did here was I plotted the northern hemisphere energy imbalance, where you see in red the outgoing long wave radiation, and then in yellow the absorbed solar radiation.
Yeah.
Which became positive around 2015, and this is the 4-year average to reduce the noise. And then you compare that to the southern hemisphere, which has been absorbing much more sunlight than the northern hemisphere was, and also radiating less heat to space because it's colder than the northern hemisphere was.
Right.
So I think and this the northern hemisphere got also about 0.6 watts per square meter darker than the southern hemisphere did.
Right.
What the same NASA series data shows. So I think that's what you're also saying, that your PhD student will also look at where these changes are happening, right?
Yeah, and I guess that's one of the key things, is that we have historically the developed world in the northern hemisphere has been first to produce to use fossil fuels and produce SO2 emissions, and we've been cleaning up. And so the cooling, the counteracting of global warming due to CO2 with SO2 was predominantly in the northern hemisphere, and that's now being reduced. So we expect to see the northern hemisphere warming more than the southern in that case. But there is stuff going on with cloud cover, I believe, in the southern hemisphere that probably is more clear. Certainly in models, I think southern hemisphere clouds become quite vulnerable to climate change in some of these models. Yeah, really interesting that, isn't it? And it is partly what you've been posting and writing that got me interested in this problem, actually, Leon, because I do think there's a lot that the climate scientists, we miss from just that planetary energy balance perspective, and the fact that we've got this wonderful data from CIRES to try and track it now over a reasonable period of time. 25 years is quite a long time in the context of the rate of climate change. So we can start to see things in it. And the dream would be that you can work out things that we would otherwise consider to be just a range provided by models, but from the observational data more and more, because we know global and we know how the energy balance has changed. And
Yeah, thanks. I think that's what caused the imbalance is really crucial, and this NASA satellite data really helps to pin that down. And I think we need much more of that data. We need more. I think we need more satellites to reduce the uncertainty and to increase coverage and accuracy also over time. And so
we're unfortunately in a position where even the maintenance of those sort of records is at threat, of course. So it's a difficult time, I think, especially in the US.
Yeah. Well, I think maybe Europe needs to start getting involved more, and maybe Japan. We have, of course, the European Space Agency and the JAXA, the Japanese Space Agency. I do think there should be more cooperation, especially on these really crucial missions.
Yeah, I think also what this is proving is that we need resilience. I mean, this data is of vital importance to the whole planet and therefore to all of us. So it feels like we need more resilience to political shocks that can happen anywhere in the world, actually. And it feels like at the moment we've got the information on climate change and action on climate change is vulnerable to sort of random events in different places around the world. And it feels like we have to become much more resilient to those, because they will happen.
Yeah, indeed. Will be interesting. I'm really looking forward to the findings of your team there, and what you will discover from these. And if you ever want to chat in more detail about more the regional impacts,
that'd be really interesting. I'm very interested also in the possible impact of the shipping fuel change, which I know you've written about, and I suspect that the standard ways of doing things are underestimating the impact. So I'm very interested in whether there's any evidence of that as that record extends, whether we can see any more evidence of the shipping reduction in SO2 from shipping playing a major part.
Yeah, thanks. I think that that's all a discussion we've had here before, and also what you were relating to this, the question of forcings and feedbacks, and what you see with these, of course, these shipping emission changes. What models often do, as I understand, is that they keep the ocean temperatures fixed, right? And then they try to look for a forcing effect from these aerosol reductions. But of course, the feedback is when the ocean's warm, and then the climate heats up, and then also the clouds respond to that, and they evaporate faster. And what are your thoughts on that? How does that? Because of course, over if a forcing is centered over the ocean rather than, of course, greenhouse gas, which have a global forcing, or but so how is then this standard way of estimating forcings?
Yeah, I think it does depend a bit on the study. So in the past, what was done was to do just that, is to imagine instantaneous impact of a change in something like SO2 or sulfur aerosol or CO2. But now I think they use this thing called effective radiative forcing more and more. So they'll do a model run with and without the effect in, and then they'll calculate a sort of estimate of the radiative forcing from the top of the atmosphere imbalance created, and also the temperature change, and some estimate of essentially the climate sensitivity, and they do it that way. And you can get that from models very easy because you know the climate sensitivity. And that's more and more what they do. So those things do include some sort of a feedback. in them to a degree, and the notion of effective radiative forcing sort of relies on a sort of timescale separation for that to operate. But yeah, I think they have got some feedbacks in them, but I guess they're not very long term. They're more like it's a diagnostic thing that you can get out of the models. And the other big issue that I've heard people talk about is the assumption about the level at which the SO2 emissions from shipping goes in. So if you put it in the lowest level of a model that might be 10 meters, doesn't stay there long and it's not high enough to affect clouds. But if you imagine that the effective chimney height is more like 50 meters, 100 meters, has a big impact. And I think they're finding that more and more is that the assumption about where you inject the SO2 probably needs to be changed, because we've got huge ships now compared to what we would have had even at the beginning of the millennium. And they've got stacks and they're shooting SO2 higher. So when you take that out, it's a bigger impact than maybe we thought before. There's all sorts of variability in the climate system as well. And we went through a huge El Nino and reasonably big El Nino 23, 24. That's an impact. But especially the North Atlantic warming looks so strong. And that's not what you'd expect to see, except in those regions that are normally affected by El Nino. It's much bigger than that. So I think the jury is still out a bit on that.
Yeah, of course. And I think that's what I realized, that many of these discussions about forcing versus feedback, I think it will keep scientists busy for a decade, I guess, right? Because it's very hard to disentangle these two things.
Yeah, it is, but it feels like we ought to be getting closer. So, I started out in climate science in the early 90s, and the signal of global warming was getting clearer, but we were still sort of basing it on theoretical ideas and modelling. And actually, it would have been bizarre if there wasn't climate change happening, given what we knew about the system. But now we're in this situation where we've actually got 35 years since then, and we've been continuing to put CO2 in the atmosphere, continuing to affect, change aerosol forcing and so on, and all sorts of other things. So it feels like we're in a different world now, where we're not crystal ball gazing with models. We're actually using models to interpret observations more and more. And one of the few pluses about not dealing with a climate change problem is it should be clear about the nature of the problem, how big it is. We should be able to do that better than we do at the moment.
I think that's a good bridge to talk about tipping points.
Yeah.
There was a Carbon Brief article where which asked a number of scientists the question of what tipping points they were afraid of or were worried about most. And you mentioned the Amazon, right?
Yeah. It's been so that comes from the first piece of work that I did. Well, the most significant piece of work I did when I was at the Met Office Hadley Centre in the UK, which is the Climate Prediction Centre. And what our team did was to produce a model that tried to couple together a physical climate model with models of how much carbon's taken up by the land and the ocean. And as I said earlier, about half of our emissions are actually being taken out by land and ocean sinks, thankfully. Yeah. And when we put this little model together, we found a rather shocking thing, which is that the land sink turned into a source in this model in about 2050 under a business as usual scenario. And the main reason for that was that increasing temperatures was projected to release carbon from the soil. Basically, things decompose faster when you warm them up. Take your cheese out of the fridge, see how fast it goes rotten compared to if you leave it in the fridge, it goes a lot faster. And the second thing, and this was very specific to that model, is that we found the Amazon forest was projected to die back, to basically just from climate change, without deforestation, just to die back. And I think that model was overly sensitive now, having looked at other things. But there are aspects of it that make sense. So what we've got now with the Amazon forest is we've got climate change going on. We've got aerosol emissions reducing, which actually has a strange non-local effect because they're in the northern hemisphere. The intertropical convergence zone tends to move northwards, which makes the Amazon west and south of the Amazon drier. Just move the intertropical.
Can you explain in 2 sentences what the intertropical convergence zone is?
So the intertropical convergence zone is essentially the band of heavy rainfall in the tropics that moves around with the sun a little bit, and it tends to move to wherever the ocean temperatures are warmest. So if you look at the Atlantic, the warmest bit of the ocean, northern hemisphere or southern hemisphere, it'll have the ITCZ, the intertropical convergence zone, move that way. So if you warm up the North Atlantic compared to the southern, especially in the tropics, you will move the intertropical convergence zone a bit north. That will have a good impact on sub-Saharan Africa. It'll get a bit wetter there, but it'll be a bad impact on Amazonia in the south, get drier. And we've found in our models that the combination of these two things is really a problem. It's probably what was going on a bit in the Amazon in 2023, when it had its worst drought ever in 2023, which is both an El Nino, which affects the intensity of the dry season, and also this warming of the North Atlantic relative to the south, which extends the length of the dry season. So
you have these rain bands, as I summarize. So these rain bands from over the southern hemisphere during the certain time of the year when the rain falls in the tropics, and it's of course it's different in different regions of the world, but where I'm in Ethiopia, where I work, it's around June, and I think in India it's about the same. That's when the heavy tropical rainfall starts, and then the Sahara is more north than the Amazon rainforest.
Yeah.
Right? So then the Amazon rainforest will have less rain, and the Sahara will likely have more rain. And of course, we saw that also last, I think, 2 years, where there was a lot of rain falling on the Sahara, right?
Indeed. And there's even been suggestions that during the peak SO2 emissions in the Northern Hemisphere that were in the late 70s, early 80s, the ITCZ would therefore have moved southwards and away from sub-Saharan Africa, and it may have contributed to those horrible droughts that occurred in the 70s and 80s that killed a lot of people. So yes, sulfur dioxide emissions seem to have had quite an impact on climate and climate impacts for quite a while. So
do you think that it's has more regional impact, as some studies suggest, than CO2 in general?
Just because CO2 is well mixed. So where you get non-linear effects of CO2, it's basically the climate system responding with a pattern to something that's fairly uniform forcing, whereas SO2 is very much dependent on where the SO2 was, where it's going up and where it's going down. So this is what we're hoping we can do with our study, is to use the patterns which are very clear with sulfur dioxide but are not so clear with CO2. But anyway, what happened in our model was that the Amazon forest did basically die. We were modeling it interactive, and it died under climate change. And it was worse when the sulfur dioxide emissions were dropping off as well, but that's a separate issue. I think subsequently we've convinced ourselves that the model was oversensitive. For example, the variation in carbon dioxide from one year to the next due to an El Nino event, which is indicative of how sensitive the model is to climate variability, was much too large. But what we have got now is we've got this combination of effects that we didn't simulate, which is that climate change is occurring, aerosol loading is reducing, and we've got deforestation and forest degradation going on at the same time. So my concern is that we're sort of approaching a boundary that you could approach by almost on the diagonal, by changing climate in a detrimental way and deforesting and such that you can reach this boundary much more easily. And I think we're seeing evidence of that in places. Fires increasing, and you get degradation around the edges. That means you can get further fires formed. And so I think that ecosystem, which is one of the most diverse on Earth, is in danger.
Yeah, I think it's already turned into a source. As I've seen research on that, and I've talked about that also in the media, where the Amazon rainforest has already turned into a net source of carbon dioxide. And what I read about, I think it was back in 2009, was that the Amazon rainforest and these rainforests in general, of course, we know very well how these rainforests create their own rain by evaporating water, and then they create these rain cycles. But some research suggests that they might also create these wind patterns by evaporating water and condensation, and then creating these very large wind patterns, which bring also the moisture. So maybe have you read about that or done research on that?
I have, and you can see it to some extent. So when we got this dieback, the forest started to die on the simulated dieback. This model dieback was on the northeast coast of Brazil. It was already quite dry, and then gradually the forest was depleted just by climate change from there and moved inwards. And that was basically rain no longer being recycled in the way it was. So Amazon trees have got big, deep roots. They can extract water from depth. They also have leaves that intercept the water and evaporate it back very easily. So they do the recycling very well. And that takes water into the middle of the rainforest. And I think there are various mechanisms like that. Some of them are not included in models. For example, models produce various types of chemicals that might lead to additional natural aerosols as well over forest. But even if we just look at the basic thing that you have trees that recycle moisture and you take them away by climate change or directly, and that will affect recycling, that's pretty clear. That's what would happen in general. And when we see this catastrophic dieback, that's sort of what happens, is that you lose a bit, therefore less water is transported to this bit, so you lose that bit. And I don't think it's quite as bad as we thought in those early models, but I think aspects of it, like with all modeling, there's an element of truth in it that we're beginning to see now.
And I think that's the scale of deforestation is also mind-boggling, and that's indeed a crucial aspect, and added to this impact of warming and reducing aerosols, also more sunlight reaching the forest and drying. So
and it's interesting, of course, that the next Conference of the Parties of the United Nations Framework Convention on Climate Change is in Brazil, so there'll be a lot of focus on forest, I think, and nature-based solutions and things like that.
Do you know by heart how much carbon is stored in the Amazon rainforest, and how much could come out in the next 100 years, even if it's less bad as you thought before?
So I think when we lost the whole forest and a lot of the soil carbon, I think it was something of order 130 to 150 petagrams of carbon, which is equivalent to current emissions about 10 or 15 years. So it has an impact, but the main thing is it totally wipes out people's livelihoods and kills people, but also biodiversity in that whole region is lost, and it's huge. So there's this thing about water being recycled, of course, and there's this thing about the carbon being released and adding to climate change. But I think that the sort of impacts on local people and wildlife probably more significant even than that.
I've traveled through the Amazon rainforest back in 2009. It's such an enormous. It covers. I don't know exactly how many countries, but it consists out of many countries where, and it's all these different kinds of forest as well. It's not just one single homogeneous forest, of course.
No, you can actually look and you can see, if you go up to one of these towers where they're measuring CO2, you may have done this, Leon, you can look over and you can see where previous El Nino events that dry out parts of the forest have killed a segment of trees and they're still standing. And then there's live ones around them. So it's a very dynamic thing, even without stresses. But you could tip it over the edge by virtue of the fact that the cycling is so close to balance, or it was when we started, that you can accelerate one thing, like, for example, fires or disturbance or drought mortality, then you can tip it over the edge. And the estimates that are coming, like the ones you mentioned, where the suggestion is that the forest from going from sink to source are generally related to not the fact that the photosynthesis is declining, but the mortality rates are going up because of increased disturbance and droughts in particular.
It's a beautiful. It's like a continent, right? So such an enormous forest, and I think that's we really need to preserve it, and and it interacts also with the other tipping points.
Yeah, indeed. So, I mean, the concept of tipping points more generally is something that's concerned us at Exeter for a long time. this idea that quite often we're thinking about climate change, we're thinking about what look like continuous things like global temperature increasing or CO2 increasing and driving that. But actually, we think there are bits of the globe, like the Amazon forest, that could go over a threshold and change abruptly to another state that might be difficult to return from. So the Amazon forest is one that I'm very concerned about. But you would have heard a lot about the Atlantic Meridional overturning circulation.
Yeah, the AMOC.
The AMOC, and the fact that this could bizarrely cool down Western Europe under climate change if there was a lot of fresh water that came in from, for example, from melting ice sheets. And we've got other ones that are related to that, things like permafrost melt and thaw, and being released. Yeah. And as always, you've got a very appropriate figure.
Thanks. Yeah, I think that this is also where, the Greenland, and where's the Amazon? So here they think it's
down.
And then that's your point also on the other stresses are not included in these models, right?
Yeah, quite right.
So
quite right.
With only climate change, the Amazon might have some time left.
Yeah. So this is an interesting thing, actually. So what the models suggest is that there's two effects of carbon dioxide increase. One is that carbon dioxide causes climate change, which is generally detrimental to especially the Amazon forest, but forests in general. But carbon dioxide also fertilizes growth, photosynthesis, and that's well-founded when you've got nutrients. And in models, that second effect generally wins, except in rare exceptions. And locally, it might not, but globally, it tends to be the case. It's probably the reason why we have a carbon sink on the land is predominantly, I think, due to the CO2 fertilization effect. So there's a kind of a war zone, this, where people say, climate skeptics believe and denialists believe in CO2 fertilization, but climate scientists don't. Carbon cycle scientists actually do, but of course they think it's very, very much constrained
because they had high school chemistry.
Indeed it does. Yeah, indeed it does. And and it's quite difficult to explain the land carbon sink without having a CO2 fertilization effect that's quite significant. But how significant is really key. So if the Amazon forest, for example, was not getting any benefit from increased CO2, it would probably have been turned into a source quite a while ago, as far as we can tell. So basically, the Amazon forest is suffering from climate change. It was already an optimum temperature. Rainfall patterns are changing. It's getting drier in places. There's more fires. There's human disturbance, as we said. And it's only the CO2 that's kept it from that to now.
And I think what's quite crucial there is, of course, what also everyone who studied ecology and chemistry knows is that the fertilization of CO2 is, of course, it's also limited by the other crucial aspects of plant growth, other nutrients and water and sunlight and all these other factors which also determine how much ecosystem or a plant or the whole global ecosystem in a way can grow, right? So we could reach this fertilization, CO2 fertilization peak in a way, I suppose, at a certain within ecosystems.
Yeah, they do. And models have different degrees of this, but in general, you expect the impact of CO2 fertilization to decline at some point. Generally, when you get to the point where CO2 is not the limiting factor, but it might be nutrients, for example, and that high temperatures can reduce photosynthesis faster than CO2 can increase them. And we do see that in models, but it varies a bit where it occurs. And so whether this critical value where you get to a CO2 level where further CO2 is detrimental differs between models.
Any other tipping points you you want to talk about, or any other or about like the range where we are now? Do you think we are, for all intents and purposes, reaching 1.5 as we speak?
Yeah, I mean, it's going to be very difficult. So the 2024 had a global average temperature above 1.5 by most reckonings. This year is the second warmest on record I've heard in the first half of the year, so it's likely to be close. We have still got CO2 going up, we've got emissions still going up globally, so it's very unlikely we're going to avoid 1.5. And the 1.5 that's sort of encoded in the Paris Agreement is probably decadal timescale. So we're not quite there yet, but it's impossible to. It's very difficult to believe that we're not going to exceed that. So I think 1.5, which was always, I hate to say it, a sort of aspirational target from the Paris Agreement, is going to be exceeded. Exceeding the upper limit of 2 degrees, because the pledges that have been made nationally, even if they're kept to, which is a big but, it would take us to more like 2.5 or between 2.5 and 3 degrees of global warming. So still got quite a lot to do, and we haven't yet. We're hoping for the last few years that CO2 emissions would peak and start to come down, but they haven't yet. The rate of growth has declined. There was a brief decline, you may know, during COVID. So we had a pandemic, people stopped traveling and they stopped doing all sorts of things. And CO2 emissions did go down for a little while, but they're back up again, and we're almost back to as if COVID never happened. So we haven't yet managed as a race to get to the point where we can get CO2 emissions under control and not have some huge trauma occur at the same time. And of course, we don't want the trauma to be climate change caused by CO2.
I think that's a good point. I think you often see in the media points where they show that we are like somewhat following the Paris goals or the Paris Agreement decrease the CO2 emissions, but they rarely write about COVID and the global energy war with Russia and happening, right? So
yeah.
Take that into account. I think that I don't see much for a downward trend.
No, not yet. I mean, for a while we've had the carbon intensity of the economy. This idea that the amount of GDP, for example, you produce for CO2 emissions is declining, and it has been declining in the developed world for quite a while, but largely by exporting our heavy industry that's producing a lot of emissions to other places and buying it in. But in general, I think it's felt that the developed world has this going down, and there's a counteracting effect from things we buy from abroad, especially from China. So I think we still haven't got that under control, and we're still in a situation where we have decarbonisation rates of the economy that are slower than the rates of economic growth, which means CO2 emissions have to go up, and that's where we're at. I'm afraid we're still there at the moment. That's the real point where you just say that's going to ultimately limit what we can do economically as well as human well-being in general.
So thanks. I'm just thinking. I send you. So you organized the. There's so much I want to ask you, but I think we don't have too much time left. But you organized the Exeter Climate Forum.
Yeah.
Is that right? The last.
First week of July we had a forum there.
Maybe there are some of the main findings you want to share.
Yeah, well, just briefly, we had two parts to this. One was the Global Tipping Points Conference, which was thinking about these issues of tipping points in the climate system, but also the notion of positive tipping. So this idea that, just like we worry about non-linearities that could cause a catastrophic change, we can also imagine things that can grow exponentially by virtue of feedbacks in the system, like economies of scale and adoption by large numbers of people, or community activities that bottom up that can also lead you the other way towards solutions. And we call these positive tipping points. And we think they're a large part of it. So for a while, I think we were thinking all the non-linearities were in the problem area and all the solutions were linear and therefore slow. But I don't think we're in that situation. Humans are capable of changing things dramatically by virtue of innovations and the way we organize. And I think there's still the chance that we can do that. But the other part of the conference was a bit more broad and mainstream at the same time. So we're thinking about how do you communicate information about climate change so that it's more effective in informing action. And we also spoke about various things like carbon sinks that we've already mentioned, and also more radical things like geoengineering, which I think is going to come up the agenda because of our inability to deal with climate change in the obvious way, which is to cut our CO2 emissions.
Yeah, you think that there will be more, or it will be on the agenda?
Yeah, I think it has to. I mean, so for a long time, the concept of doing this aerosol cooling deliberately, either by putting sulfur dioxide in the stratosphere, which is something some volcanoes have done in the past, like Mount Pinatubo, or by brightening clouds through spinning up sea salt. It sounds crazy, but it is a fast way to cool the system. We don't know many of those. So even though I wouldn't advise doing it, I do advise doing research on it, and doing research on it in a way that's above board, because at the moment there's a sort of stigma associated to that research that means it's been driven underground, and that's the worst case scenario. You know, if things like that are going to be done on the climate system, people need to be aware of and need to be engaged in a debate. So I'm very much in favour of us pushing it above ground. It's been above ground at various times, but in relatively small groups of people and not discussed. I think it needs to be discussed, and it needs to be researched long before it's done, really.
Yeah, I think that's been a quite, to me, quite a scary thing to see, that there's been some, and I won't mention names here, but there's been quite some scientists writing open letters or writing media articles objecting to do scientific research. And I think that's and we really need this research to reduce risks, right? Because the last thing we want is to have whichever party do intentional geoengineering.
Yeah, it's a very widely held view, though, that actually by climate scientists, that somehow discussing the possibility of something that you might do, as they see it, instead of cutting emissions, which I don't think it should ever be that, would somehow reduce the tendency for people to act on their emissions and to deal with the root cause of the problem. But we had it in the UK. We had a Royal Society report on this in 2009, many years ago now, 16 years ago, and we did a brief survey of people when they knew nothing about geoengineering, and we spoke to them about it, and we said that here's the climate change problem, here's this geoengineering thing that you might do. Are you more or less likely to act on it? So this is what social scientists call the moral dilemma, morale dilemma, which is a moral hazard, which is this idea that if you have some safety net, you'll probably take more risks. You know, it's a bit like when seatbelts became legally obligatory in the UK. For a while, people drove more crazily and more pedestrians died. That was the idea anyway. And so this is the idea that if you have a fallback position, that means it's not as dangerous as you thought you were in act. But actually, you know, we got the opposite response, which is that people said, if those crazy scientists must be thinking of doing something like that, this must be serious. Yeah. So it was an odd thing that it had the opposite impact. And I think the issue is that you don't have to be doing it, or you shouldn't be thinking about doing it instead of cutting emissions. That's the primary thing you have to do. But if, going back to our first point, some of the warming is due to something good we did, which is to clean up the air, maybe there is a case for counteracting that temporarily, and then bounding it by that. You don't do it instead of cutting your emissions, but you do it instead of getting hit really in the face for doing something good, which was to improve air quality.
I don't think there's anyone really promoting geoengineering instead of cutting our emissions, right? There's maybe some fringe, but those who want to do the research on geoengineering or sunlight reflection methods or whatever you call it, they want to reduce risks. They want to. I think that's the goal, and I think that in a way that it's often a straw man to say we shouldn't do research because there might be some, even if, as you mentioned, the science is against it. The science says if you talk about geoengineering or you do research on geoengineering, that might increase urgency. Then it's still used as a straw man or as a, and I think that's to me that's really dangerous. I would be interesting to hear what you think about climate scientists saying that we shouldn't do climate science.
Yeah, I'm opposed to that too. I do know why people say it, because those people are often in a situation where they've been trying to just get people to take the greenhouse effect seriously and the CO2 problem seriously to deal with it. And so they don't want anything to dilute that. But I think we're also in a situation now where we're obliged to think about things that might be considered emergency measures at some point, and to think about how we might develop such a thing. Like with an ambulance, you don't have ambulance because you want to have an accident. You have ambulance because you might. And I think we're getting to that stage now. So I do think we should think about that. And a lot of this work is about modelling and about technology developments that don't require you to make actions on the real world system. I mean, some of them are pretty benign anyway, like blowing sea salt into marine stratocumulus clouds. I mean, you can definitely do that. And it went on for a while in San Francisco Bay, I think, until people realized why it was being done. But we do need more data on it, but I don't think we need to modify the system. We just need to done the background research, partly so that someone could do it now and it wouldn't even be illegal to change the world's climate by doing these sort of things, like putting high flying aircraft and putting sulfur dioxide in the stratosphere. It wouldn't strictly be illegal. So we need to get that discussion and that research done above board and a proper discussion about it so that people know what's going on and it's not in the hands of a few again, which is one of the problems we've had with the world for a long time.
Yeah, and in a way, to sum it up in a way, is saying, should we find a way to be able to save the Amazon if what we've been doing fails?
Yeah, indeed. And I think that you can't, one of the things you have to do is stop chopping it down, but you can counteract to a degree for a while the impacts of global warming, we think. And that was going on in the Amazon. So what's going on in the Amazon is declining. And you wouldn't want to put the SO2 back in this lower atmosphere where we breathe it and where it affects atmospheric chemistry, but you might want to do other things a bit more benign.
Increase natural sources of aerosols might be a way. And then do more research on stratospheric.
And more and more now people are interested in marine cloud brightening because it's more local, but it does have consequences because it's therefore a forcing that's patchy, and that can have impact on circulations. But I think it's worth studying, and some of the modelling results are quite impressive on that. So I just think it needs to be above board and discussed and not considered a taboo. And so, like you, I'm very much against it being driven on the ground again, because I think that'd be the worst thing that could happen right now.
Thanks. Well, really great talking to you. I think there's let me get Stacey on. As I mentioned, I have many questions, but I also want to give the people on YouTube a chance to ask some more questions. So, hi, Stacey.
Hi, Leon. Hi, Peter.
Welcome back.
Thanks. Yes, good to be back. The one thing that struck me, Peter, is a couple times you said this, and I'm sure it's very common in your space, but you were saying the natural background of SO2, and that, well, these are in places where there is no natural background, etc. And I just, it's hard because this gets to the geoengineering argument. There is no natural. Everything we're doing is unnatural. And so it's just a matter of why wouldn't we do the thing that is less harmful to us and all other life on Earth?
So the background in that case was to do with, there are some natural sources of sulfur that produce aerosol, and they come from the ocean largely. So there's a whole theory called the claw hypothesis, believe it or not, which is that that's marine phytoplankton produce dimethyl sulfide, which produces SO2 aerosols. So that's the sort of background you might think about. And normally that's tiny compared to our emissions. And most of the things we do, you're absolutely right, Stacey, just swamp the natural background. But there are some things where the natural background matters because the changes we're making are relatively small. So the fact, if there was lots of natural background, it would mean nothing at all. But if there was no natural background, it could be a big thing.
But
so this just,
when you're referring to that about the natural background, you're talking about the planes doing this.
No, I'm talking about, in this case, so this is over the ocean, I'm talking about the fact that phytoplankton would produce this DMS anyway.
Yeah, there's about 20 million tons of sulfur dioxide being emitted already by the life in the ocean. That's the background source of sulfur.
So this is natural in that sense.
Okay. All right. Sorry, my misunderstanding. I thought you said planes. And
so planes are would be used if you were going to do this deliberately. You'd probably use something like high flying
Oh,
planes
yes.
to do it. Very high.
Okay. Sorry.
Yeah,
I
yeah.
was
I was
getting the cart before the horse there.
No worries. No worries.
And that brings us, so Tom was saying something about, why don't we just put the genie back in the bottle and put sulfur back into fuels?
Yeah.
That would probably appease all of the absolute lunatics we have in places here, like here in the US, who are wishing to outlaw any even research of it.
Yeah. So the reason we, and Tom probably knows this, the reason we wanted to remove sulfur from fuels was because it had a bad impact on chemistry, produced things like acid rain, but actually makes the rain acid, which has its own impacts, but also SO2 is chemically active, so you change atmospheric chemistry. So there's lots of reasons to do with just breathing the air that we don't want sulfur dioxide in the air.
Oh, sure. But his follow-up point was, the life on Earth may end. So does it matter if we have clean air, that kind of thing?
Yeah, I don't think life on Earth will end, actually. I think the biosphere is very adaptive, but I think it could easily become, and is becoming, less favourable for humans. I think it's humans that are really at risk here. And there are bits of, we've spoken about the Amazon forest, there are bits of the natural biosphere that are definitely under risk because of us and the things we're doing. But I think the biggest issue is, how do we make it remain habitable for us to thrive as a species? And I think we're in danger of pushing it beyond. We're in a lovely place for a while. We've been in a lovely place for a long time, and we're pushing it out of this place into a place that's less favourable for many of us. And it feels like we should just stop doing that.
Right.
It's easier said than done, I know, but yeah.
It's hard to imagine that the climate has been stable for almost 10,000 years, right? It's been really well.
Yeah, it seems like civilization emerged in a time when the climate was peculiarly stable, actually, in Earth history. Yeah.
And I apologize for that species-centric view of life ending. It wouldn't be all life. It would, I'm just thinking more along the lines of most of us. The one thing the devil's therapist said that I totally agree with, I'm like, how can we get all this together? Is there an open sourcing that everyone working on this could use in terms of the models? It does work a lot in the tech field.
You mean in terms of the results that are coming out of models?
Well, in terms of the inputs of the models, and then everyone being able to access and run their own, it seems like a lot of the models are, I mean, not that anyone's trying to hide it, but it does seem like things can tend to be a bit siloed. And I would think we could get places faster if, like he's suggesting, there was open sourcing.
Yeah, so most of the models, these climate models are huge things. They take a long time to run on very powerful computers, but the data from them is available. And in the past, we've had things like, there was a thing called climateprediction.net, where people could run a climate model of their own as a sort of screensaver on their laptop and produce their own simulation that would go into a whole array of simulations, and we could look at the possibilities of certain extremes happening and things like that. So there are kind of public participation things like that you can get involved in. There are also more and more emulators now. What AI is allowing us to do is to get much faster emulators of very complex models, which means that more and more people can play and say, well, what if this happened or that happened? And I think they will emerge more. I mean, as part of the communication problem is, how do you get people engaged? Is to basically say, stop telling them this is how it is and let them find out for themselves. So I think that's one of the things where AI and machine learning is going to help, Stacey, I think, in that respect. And if it engages more people in it, all for the better, really.
And that feeds in nicely to what, I'm not sure if it's Jerome or Jeremy was saying. Has anyone asked AI to give an exhaustive list of positive feedbacks? He suspects it's over 300 and accelerating with each passing week.
I haven't done that. It's a really good question. I suppose you could do it actually now. You're probably doing it now, aren't you, Jerome? So yeah. Be interesting to see whether there's a runaway feedback in the number of positive feedbacks. Would be a bit scary if that were the case. A lot of these things are sort of renamed, I think. So the ones we worry about in the climate system are still things like water vapor feedback, which is that water vapor itself is a greenhouse gas, and as you know from high school chemistry, if you have a warmer atmosphere, it holds more water vapor. So the primary positive feedback is that one, just that warmer atmosphere holds more water. Water's a greenhouse gas, it amplifies the change. And then we've got these other things and more obvious things, like some other people said in the chat as well, that we shouldn't forget the fact that when you warm up the climate, you melt ice and snow, which makes the planet darker. So that's part of it, but it doesn't look like from the satellite record that's the primary thing. It looks more like not that surfaces are getting darker, but the clouds are getting darker, which is an interesting thing to see in the satellite record. But yeah, it'd be an interesting thing to do that. If you do that, it'd be interesting to see the result, how many things that AI can come up with. And you can probably come up with your own.
Down in the comments. Share it down in the comments.
Is it down there?
Well,
yeah.
I'm just saying, like it.
Yeah.
I'll just ask one more to follow on to that, and then we should go to Eli. But so what do you think the efficacy of solar radiation management versus marine cloud brightening?
So marine cloud brightening is a kind of solar radiation management. But
sorry, I should have said sulfur injections, which is what I think we typically go to.
Yeah. So the sulfur aerosol injection, we sort of have some proxies for it because it's what volcanoes like Pinatubo did, and it might have cooled the planet by 0.5 degree during that period in 91. So we have an idea about that, and so marine cloud brightening, the advantage of it is that you can do it without changing the whole planet, hopefully, but you can imagine there's even some modeling experiments where they're just trying to inject sea salt into different parts of the globe to try and get a balanced response. Solar radiation management in terms of sulfur aerosol injection has this proxy that it looks like what volcanoes do, and it gets very well mixed. Once it's in the stratosphere, you inject in the southern hemisphere, it's kind of like half a basketball of color change, right? So the whole thing gets mixed around. So it's a much cruder instrument, but it is probably the most obvious way to cool down the climate quickly if you get the SO2 up there. So more of an emergency measure, I think, really, than anything. And we have some background in understanding what that would do to the climate system, good and bad. And what you need to avoid is imbalances that produce a change in where these tropical rain bands are, really. But yeah, I think if you wanted to really cool the climate system down, it would probably be sulfate aerosol injection at the moment, or stratospheric aerosol injection. But if you wanted to do experiments that would not change the planet and would not affect too many people, it's probably marine cloud brightening at the moment, and people are thinking about that because it's much more benign. You basically imagine blowing seawater up in the air high enough that it evaporates and you're left with sea salt, and that will brighten clouds or reflect sunlight. And there are some experiments already being planned on that, but they're very, very local.
Yeah, there's already some small experimentation happening over the coral reefs in the Great Barrier Reef, and of course there's a lot of I think there's a lot of license to operate there because they really want to keep the coral reefs, of course, from disappearing.
Yes, and coral reefs are an interesting example. We looked at very early geoengineering experiments with models, and we found that the experiments where climate changed, but it was counteracted by SRM, actually stratospheric aerosol injection, the coral reefs did best of all. And that was because you could actually lower the temperature locally more than you would do easily with mitigation, but still a huge thing to do. And you wouldn't want to be changing the whole climate of the planet for the coral reefs. You probably want to do something more local. So marine cloud brightening makes more sense. But also there's a thing called clear sky brightening now, Leon, which is that you can, imagine if you throw sea salt up, you reflect sunlight even if there's no clouds. Some modeling experiments show that can be quite effective. I don't know what it does to the visibility. I think it's probably not very good for the visibility. You don't get nice clear days anymore, I don't think.
Yeah, but it would help indeed for the coral reefs, because they especially when it's very hot, the direct sunlight impacts the coral reef a lot. So then it really helps if there's less sunlight reaching the corals.
Yeah, and they are probably the reefs. We spoke about tipping points. The reefs are probably the closest to their thresholds, and they are getting bleached regularly anyway. So I think that's where you would need some sort of local emergency measure, if anything. Yeah.
Thanks.
Can I just ask people that, because we don't do it often enough, to like this broadcast and to share with your friends and family, and to subscribe to the channel so that we can get more reach, and then also turn over to Eli as well.
Yeah, thanks. And you can share this video later. The link will still be the same, and you can people can watch it. We get the most views after the live stream. Indeed, Eli. No video, but here's Eli. You have a question for Peter?
Thank you. So you covered part of what I wanted to comment on about coral reefs, but there's a further complexity to the climate system, the biological components of the climate system, where coral reefs and phytoplankton, they adapt the level of their sulfate emissions naturally. And I kind of wonder how much that confounds what you discussed earlier about it being less important, because they probably have been emitting less because we've been emitting more, and consequently they might wind up emitting more if the population genetics haven't changed as we emit less.
Yeah, I mean, there was, I don't know whether you're referring to this, but this claw hypothesis, that was one of the things that came out of Jim Lovelock's mind, and some aerosol specialists actually, is this idea that if you warm up the planet, phytoplankton may produce more dimethyl sulfide and therefore reflect more sunlight and cool the planet back down again. And it was quite heavily studied. I think one of the issues was that there wasn't so much evidence that SO2 DMS emissions, this dimethyl sulfide, was actually going up with temperature as envisaged. I think more recently it's been found that it probably goes up with micronutrients like iron. So you might put in iron in that people think about doing to remove CO2, might also increase DMS emissions, which would have a net impact. But I sort of feel that with the biosphere, that it's if it's set up to do anything, it's to maintain its function, in a way that sort of Gaian ideas promote, but it isn't there to counteract us. So in general, the biosphere would be quite happy if we weren't here. I'd probably be.
There was one observation that I'll point out. Alva on coral reefs, there is actually a threshold temperature at which it can no longer quite put out as much dimethyl sulfate. It tries, and then it just
and I guess that's almost a definition of a tipping point, really, isn't it? As you get to a certain threshold, and the feedback loop no longer operates. And Lovelock himself, who was a brilliant man, he was of the view initially that the planet would look after itself, but that the feedback loops that maintain a good environment and a good climate for life on Earth would eventually break, a bit like a thermostat breaking in your home, and you can no longer regulate, and then suddenly things go up very rapidly. And that's indicative actually of systems that are kept in balance up to a certain point until the thermostat breaks. And it's also quite a good analogy to this idea of a termination shock. So imagine that we did keep the planet cool and counteract CO2-induced warming with a sulfur aerosol injection, and then for some reason we stopped that, like someone shot down the planes, or there was a pandemic and meant we couldn't get them up, then the climate would go to where it would have been, but really rapidly, and that would be more damaging. So I think with all these regulatory systems, it's kind of like, great if they can be maintained, but you don't want to be dependent on them being maintained forever. And with the geoengineering thing, and a bit like your case with natural DMS emissions, you sort of want to make sure that in the event it fails, it's not catastrophic.
Yeah, because nature has never dealt with anything like it, where we increase the greenhouse gas forcing by 4 watts per square meter instantly, right? On a geological time scale. And
yeah, it's huge. Yeah,
there's no proof that nature will be able to help us reduce impacts for the rest of the century. I think that's also what your Going back to that, what your 2005 paper was about, also, where that the carbon sinks, it turns into a source, and we already see quite some signs about that. And I think that's to me that's one of the most worrying indications of. And then going to that, do you think that it's? I asked this already, but maybe you can like give a percentage or just so the 6 degree or higher temperature. What are the chances we could reach that? Do you think?
I think it's unlikely, because I think even if we went on a fossil fuel intensive path, which we've been on, then I think the climate sensitive is not high enough for that. And so in those days, I thought it could be much higher than it is, but the evidence is stronger for that. But it does depend on whether this darkening is due to feedbacks or forcing. So I do, there's still a possibility that it's very high, but then it would be at odds with what you said, Leon, which is that we had this very stable climate when human civilization developed, and it wouldn't have been like that if there was a huge climate sensitivity. There would be natural fluctuations that were huge. So I think
what we think, but so what we published also in the global warming in the pipeline was that the aerosol forcing and the pre-industrial human-caused aerosols might have helped to keep the climate relatively stable over this period, because greenhouse gas increased. So you would have expected the temperature to go up based on the CO2 and the methane concentrations which are found in these ice bubbles. But what we estimate is that the aerosol grew linearly, more or less, with these greenhouse gas forcing, which helped to keep the climate relatively stable. And you're right, there's of course also this variability. But we did see some of that, of course, with the medieval warm period, and of course it's more regional. But
so there's indeed. So one of the things that we're getting to grips with is that if the system's very sensitive and the feedback loops are very strong, then it'll also show in year-to-year variations. So that sort of stability that you speak about there, if the climate sensitivity was really high and the carbon cycle was as sensitive to warming as we think it is, then if it's really, really high, the oscillations are enormous to the point where the thing can be unstable, and you wouldn't have seen that stable climate. I mean, you'd have to have been very knowledgeable to be able to counteract that, even if you were exactly emitting aerosols. So there is a kind of a constraint on how large these things can be based on how much they naturally vary. And there's a whole field of this. You've probably heard about fluctuation dissipation theorem. It's a fancy name for the way things vary, tells you something about how sensitive they are to external factors like human inputs. I think we're not using that as much as we might, but doesn't stop. Still a possibility that sensitivities can change. We generally assume they don't much, but they can. And when you have a tipping point, you basically go from sensitivity blows up to the point where the system goes unstable and it goes to a new state. So that's still, that's still feasible. Certainly in parts of the system, we think it does happen.
Good point. I'll look into it in more detail. Very interesting to see how that can help to understand this. What we're seeing now. Of course, we see it now with these spikes, and it's interesting to learn more about how much of that is natural variability versus the trend reaching these thresholds. Well,
on the topic of thresholds, there was this kind of debate that we were having, including on Climate Chat, about the soil response. There's a paper, I think in 2020, Varney et al., that showed a huge potential soil carbon turnover, including under permafrost. And there was some back and forth, and the answer that was given later by leading climate scientists was that, biological fixation in the soil would also go up. And I started digging into the models that were being cited there, and it was an ensemble of models. And it turned out that only one among them explicitly modeled the nitrogen and phosphorus cycles. And that one had the lowest soil uptake. What I wanted to ask you is, do you have any feel for like how how the tail ends of these distributions might be what actually gets us.
Yeah, I mean, you're right, of course. So with climate change and certainly an environmental change, it is the extreme events that get you in the end, heat waves in the case of warming, or droughts, or floods in the case of hydrological cycle. I think I know the Varney paper because I might have been a co-author on it. Rebecca Varney was my PhD student, as it turns out. And I think the paper you're talking about has a range of possible responses of soil carbon turnover time to temperature, and we inferred them from large-scale variables we could get out of the models, and some of them look very large, and then we constrained it to say that they weren't very likely to be true. So this is one of these things we call emerging constraints, which is that you find something in the observational record that you can see in models, and you can look at in the models at how that thing that you can measure relates to what is predicted, and so you can reduce the uncertainty. So I think we have a rough idea of how much soil carbon is released more quickly when you warm up. There's a factor called the Q10 you probably know about, which is if you increase the temperature by 10 degrees, roughly speaking, the rate of decomposition goes up by about a factor of 2. So you can massively accelerate the rate at which carbon comes out of the soil and back into the air. And in the limit where you've got a very high climate sensitivity to CO2 and a very high sensitivity of decomposition to temperature, you can actually have an instability, a climate carbon cycle instability, which relates a bit to what I was talking to Leon about just then, that means that in order for the climate to have been stable in the past, we can't quite be in that parameter space, or we wouldn't have seen the stable climates we were able to thrive in. But it does mean that these feedbacks kind of constrain each other. If one of them gets really large, then you would expect to see something like an instability. The other one's large too. I don't know whether that answers your question. It probably doesn't. But there are ranges in models that that are large in some of these things, like climate sensitivity or sensitivity of decomposition to temperature. But we can sort of constrain them for the reasons that we were discussing before, which is that we've actually got a record now that's quite long. We benefit from the fact we haven't dealt with climate change, so we can actually tell more and more about what it means. Yeah.
Well, thank you very much, Peter.
Well, that provides insight.
Thank you. It's a pleasure.
Thanks.
Well, Dan Miller will be back next time. I don't know exactly the date, but if you subscribe and hit the bell button to YouTube, you will get a notification when it will go live, and you can follow us on different media, social media. Thank you again, Peter. Really a pleasure to talk to you.
Thanks.
Thank you for all your insights, and have a good dinner.
Thank you. Cheers.
Bye.
Nice to see you. Bye.
Bye all.